So in this lecture I am going to explain that how the concept of retiming can be used to reduce the clock period time of any given DSP system. So starting with this system again, three versions of an IIR filter represented by yn is equal to a of yn minus 2 plus b yn minus 3 plus xn, and the retiming was previously performed using cut set retiming. So in this graph, this was the cut set, and we have performed the rearrangements of delay element along this cut set. And in this graph, this was the cut set that we have chosen to rearrange the delay elements. Okay, now talking about their critical path time. So for graph A, this is the critical path, and it can be given by adding their computation time, so Tm plus Ta. So if the Tm is equal to 2 and Ta is equal to 1, again I am assuming that Tm is greater than Ta because it is shift and add operation and it is simple operation. Okay, so adding their computation time, the critical path time is 3. For this circuit, this is the critical path that consists of two adders, so Ta plus Ta, that is 2. And for this circuit, this is the critical path, so Tm plus 2Ta, so this is 2 plus 2, that is 4. Okay, so if you have to choose one out of the circuit, and the constraint is that it should have a minimum clock period time, so obviously you will choose this one. Now we have obtained this circuit by performing cut set retiming, and in that we have to choose feed forward cut set, and then we have to rearrange the delay elements accordingly. Okay, that we have already discussed. So that approach is good for smaller graph. So if the number of nodes is less, if graph is less complex, small, that approach is fine. But what if the graph is having thousands or millions of nodes, like in VLSI circuit? So in that case we cannot apply this cut set retiming, and then we have to look for EDA tools. This retiming will be done by then some software tool, and for this tool we have to develop some code or algo. Okay, so in that sense we will see a approach, a kind of algorithm that can be used to retime any given graph, and at clock period of this retime graph will be reduced as compared to the given graph. So now again repeating that, we have to reduce the clock period of any given DSP system, and that in turn can be achieved by minimizing the critical path, and critical path can be minimized by inserting delays elements in between. Okay, so the main thing that we have to keep in mind is that by inserting delay elements in between or rearranging the delay elements along the edges, the functionality of the system should not change. So you can compare these two graphs. I will start with this graph, and my aim is to retime this graph to this one. Okay, and critical path time of this graph is 3 and this graph is 2 if Tm is 2 unit time and Ta is 1 unit time. You can compare these two graphs. The only difference is that weight of the edges, okay, weight of edges are different, the remaining things are same. Okay, so the first step is that you have to calculate the iteration bound. Okay, and iteration bound for this graph, this is the given graph, I have to retime this, and iteration bound for this graph is 2. Okay, this can be calculated by using LPM or MCM method, and it can also be calculated by using a simple formula, that summation of computation time in a loop divided by number of delay in a loop, and select the maximum one. Okay, so why we are calculating this? Because no matter how much critical time is reduced, iteration period will not reduce beyond t infinity, that is iteration bound. So suppose you have critical path, so for this circuit you have critical path time equal to 3 unit time. So if you reduce it to 1 unit time, then to the iteration period of this graph will be 2 unit time. So this is of no use reducing it from 3 to 1. Our aim should be that from 3 unit time it should be reduced to 2 unit time. Okay, we should not aim it to reduce beyond that. We will unnecessarily put extra effort and that will be of no use. Okay, so this is the limit, this is the lower bound to the critical path time, and also t clock minimum will be reduced to 2 unit time. Then after that we have to define this graph quantitatively. Okay, for that we will define few terms. So WR U to V is weight of the edge from node U to V in the retime circuit, and W U to V is weight of the edge from node U to V in the given circuit, and WR U to V is equal to W U to V plus RV minus RU. Okay, so in the retime circuit, okay, already mentioned that the only difference is that weight of the edges is changed, and this weight is representing number of delay elements. Okay, and retiming can be done by altering the delay elements. So correspondingly we have to calculate the modified weight that will represent the delay elements between the computational units. Okay, and we have to calculate WRU2, that we need to calculate finally the weight of the edges in the retime graph, and that can be given by WU2V, weight of the edges, weight of the edge in the given graph, plus RV minus RU. So before defining RV and RU, I would like you to carefully observe these three different versions. Okay, so this was the given graph, and this was retimed by rearranging the delay element along this cut set. Okay, and this was retimed by rearranging delay element along this cut set. Okay, so if you carefully observe these two graphs, here you can see that you are taking out a delay element from the outgoing edge of node 2, and you are adding the delay element to the incoming edge of the same node 2. Okay, so in this graph what you have done, you have removed the delay element from outgoing edge of node 2 and you have transferred it to the incoming edges. So as a result there is one delay element at this point and one delay element this point, and further you have transferred this delay element from outgoing edge of node 4 to incoming edge of node 4. So now the delay element is 3D, and finally at this point there is 0 delay element. Okay, so what you are doing, you are taking out delay element from outgoing edge and you are adding the delay element to all the incoming edges of that particular node, and you are doing this for all the nodes. Okay, so this is the concept of RV and RU. Suppose this is node U and V, and this is connected via edge, and wu to v is given 3, and now we want to retime it. Okay, I am not drawing the other part, I am only focusing on this two nodes. Okay, so let's say that outgoing edge of this node v is having a delay of 4d, and this is incoming edge with respect to node v, and it is having 3d. There are other incoming edges, and for this node this is outgoing edge and these are incoming edges. So so suppose if I remove two delay elements from this edge, so new weight will be 2d. Okay, so this much amount of delay element I have to add to all the incoming edges. So this will be 2d, this will be 2d, and this will be 3d plus 2d, that is 5d. Okay, so I have performed retiming at this point, and by some means I got to know that two delay elements should be removed from the outgoing edge. Okay, so similar amount of delay element should be added to the all the incoming edges. By performing the same retiming, say that one delay element should be removed from this outgoing edge. So now the weight of edge will be 4d, one delay element is reduced, and the weight of all the incoming edges will be increased by 1d. So in this case previously there was no weight, now it is d. Okay, so what will be the new weight? WRV. How can we define new weight? WRV. Okay, so initial weight before performing retiming plus RV, number of delay element that will be transferred from outgoing edge to incoming edge, this is RV. So this much amount will be added to the previous weight. This is number of delay element transferred from outgoing edge of V to all the incoming edges. Okay, so this result you obtain when you performed retiming at this point by following the algorithm that we are trying to develop here. Okay, and now if you will apply the same algo at this point, okay, so some delay elements will be transferred from outgoing edge to the incoming edge of node u. Okay, so that amount will be subtracted from this, so this is minus r. So this was originally present, that is 3. Okay, RV, two delay element transferred from outgoing edge of V to its incoming edge, so 3 increased by 2, and then at this point one delay element transferred from outgoing edge of U to incoming edge of U, so subtracted by 1 minus 1, so this is 3 plus 2, 5 minus 1, that is 4. Okay, so this kind of approach we have to apply uniformly on all the nodes. Okay, suppose you have n number of nodes, so between every pair of nodes we have to apply this approach, and the final end result will be a proper retimed graph. Okay, so RV can be defined as a number of delay elements transferred from outgoing edge of node V to its incoming edges, and RU can be defined as a number of delay element transferred from outgoing edge of node U to its incoming edges, and WRU to V, that is the weight of edge between U to V in retimed graph, is given by WU to V added by RV subtracted by RU. So this is already given. You can obtain it from the graph. You have to find RV and RU. Okay. So using that formula, we can write mathematical equation for all the edges. Okay. So we have 5 edges. So we have to write 5 different sets of equations. So WR1 to 4 represents weight of H between node 1 to 4 in the retime graph. So WR1 to 4 is W1 to 4 plus R4 minus R1. So W1 to 4 is 2 and R4 minus R1 is unknown, and WR1 to 3, this is weight of H between 1 and 3, and R3 minus R1, and W1 to 3 is 1, so 1 plus R3 minus R1. And similarly you can write equation for all the pair of so similarly you can write equation for all the edges between corresponding pair of edge nodes. Okay, so now R1, R2, R3, R4 are unknown, so this values has to be find. If you anyhow find this value, this can be this can be calculated. And before calculating these values, you have to also keep in mind that our aim is to reduce the clock period, and you have to find these values in such a way that the clock period should be minimized.